this video, we will discuss maxima and minima worded problems. We will follow 5 steps here. Step 1, draw if needed. Step 2, identify the parameter to be maximized or minimized. Step 3, prepare appropriate equations. Step 4, reduce to one variable. Step 5, differentiate, equate to 0, and solve the unknown parameters. Example number 1. The sum of two numbers is 30. Find the numbers if their product is maximum. So for our step 1, no need to draw or no need to provide drawing for this problem. So we will skip step number 1. For step number 2, identify the parameter to be maximized or minimized. In this case, the parameter is the product. And this product is to be maximized. Step 3, prepare appropriate equations. So the involved equations here are, first, the sum of two numbers. And it is represented by x plus y. X is the first number, y is the second number. And the sum is 30. Another equation is the product. Product here is x times y. Step 4, reduce to one variable. So we will reduce to one variable these equations, the equations from step 3. So here, we can get the equation for y. Y can be represented by 30 minus x. Then substitute y in this equation, the equation of p equals xy. Therefore, step 4 is p equals x times 30 minus x. And this is also equivalent to 30x minus x squared. Step 5, let us put step 5 here. P equals 30x minus x squared. Differentiate p with respect to x. So we have dp over dx equals 30 minus 2x. Then equate dp over dx to 0. So we have 0 equals 30 minus 2x. Then solve for x. X here is equivalent to 15. Therefore, if x is equivalent to 15, we can solve for y using this equation. So y is also 15. Example number 2. Find the height and radius of cylindrical tank that requires minimum amount of material with known capacity. So in this case, we will provide step number 1, which is the drawing of the cylindrical tank. So this is the drawing of the cylindrical tank. Okay. This is the radius. This is the radius R. And this is the height H. the capacity here is the so-called volume. And volume is equivalent to base times height. Base of this drawing is in the shape of circle. So base is pi r squared and multiplied by height. Then, with respect to step number 2, identify the parameter to be maximized or minimized. In this case, the required parameter is to be minimized. And that is the amount of material. So, the amount of material is the so-called total surface area. So, this is to be minimized, the total surface area. Let us represent this TSA, total surface area, into one variable or letter. Let's say M. And the total surface area of cylinder or cylindrical tank is its lateral area plus twice of its base. 2B because the lower base and the upper base. That's why this is 2B. Lateral area is equivalent to the circumference times height for this cylindrical tank plus 2B. Circumference is equivalent to 2 pi r, then you still have h, plus 2. Base of the cylindrical tank is pi r squared. So this is another equation for M. Again, M is the total surface area. So in this case, we have two equations, the volume and the total surface area. So we have two equations that we are going to use to perform step number 4, reduce to one variable. Since the capacity volume is given, so this is a constant value here. So we will replace or we will solve H in this equation. So H is equivalent to volume over pi r squared. Then we will substitute H in the formula of M. M is 2 pi times r, and then we will put this H here, V over pi r squared plus 2 pi r squared. So we can cancel this 1 r in numerator, 1 r in denominator. So M here is only 2v over r plus 2 pi r squared. We can now differentiate this equation. So this is derivative of M with respect to r, and this is the derivative of 2b over r, or the derivative of constant over any variable is negative of that constant over square of the denominator plus this is 4 pi r, as simple as power formula. After differentiation, equate this to 0. So we have negative 2 over r squared plus 4 pi r. Then solve for the unknowns. So first, we can solve here the formula for r. So this will become 2b over r squared equals 4 pi r. So So this is, let us perform cross multiplication. So therefore, in this part of our solution, we can conclude that r is the cube root of v over 2 pi, because this portion can be reduced to v over 2 pi, and this cube can be transferred here. It will become cube root. So this is cube root or raised to 1/3. So we can say that this can be used to solve the radius of this given scenario. So this is just only for the radius. How can we solve for the height? Height is given by this equation. So to solve for h, we're going to use this formula. So h here is simply v over pi r squared. Example number 3 is an application of example number 2. So the problem is, a closed cylindrical tank has a capacity of 300 pi cubic meter. Find the height and the radius that will require the least amount of material. So this is the illustration of our cylindrical tank. Okay, so this is the radius r and this is the height h. The capacity is the volume, which is equivalent to 300 pi cubic meter. So from example number 2, we derive the shortcut for r with respect to this scenario. R is volume over 2 pi raised to 1/3. So this shortcut is applicable in finding the radius and height of a cylindrical tank that will require the least amount of material with known capacity or volume. Then to solve for h, this is equivalent to volume over pi r squared, wherein r is from this equation. So let us now solve r. R is volume, which is 300 pi over 2 pi raised to 1/3. And the answer here is 5.31 meters. So this is the radius of this problem. To solve for h, we will use this equation. So v over pi r squared. V is 300 pi, then over pi r squared. And this is equivalent to 10.64 meters. So this is our h here. So this is our r, 5.31 meters, and h, 10.64 meters for this problem. Example number 4. Finding the height and radius of the maximum cylinder that can be cut from a cone with known height, capital H, and radius, capital R. The illustration for this problem is, we have a cone, and inside the cone is a cylinder. The radius of the cone here is represented by capital R. The height of the cone here is represented by capital H. So we have capital R for the radius of the cone, capital H for the height of the cone. For the cylinder inside the cone, the radius of the cylinder is small r. The height of the cylinder is small h. Taking the side view of this drawing and half of it, we can illustrate a similar triangle. So this is the triangle. Take the half, isolate this. So this is the side view. So we have a bigger triangle represented by this side of our initial drawing. So this bigger triangle has a base of capital R because of this initial drawing and has a height capital H. There is a smaller triangle here that is similar to our bigger triangle. This is the smaller triangle and illustrated in our isolation as this. This smaller triangle has a radius of small r, or the base. The base of this smaller triangle is small r, and the height of this smaller triangle based from our initial drawing is equivalent to this capital H less the smaller h, that's the height of our smaller triangle. Using ratio and proportion, base over the height, we have r over h equals the smaller triangle base over height, small r over capital H minus smaller h. This is our first equation here. The second equation is with respect to our step number 2, the parameter to be maximized or minimized. So in this problem, we are going to maximize the cylinder, meaning its volume. So the formula of the cylinder in terms of volume is base times height. The base of cylinder is equivalent to pi r squared times h. So this is the volume of the cylinder. We already have two equations, the ratio and proportion equation and the volume formula of the cylinder. With respect to step number 4, reduce to one variable, it is better to replace h in the volume formula. So we can get h from the ratio and proportion. And this will give us small h equals capital H times 1 minus small r over capital R. Let us substitute this small h to the volume of cylinder formula. So this is pi r squared, then replace h by this. So this has h quantity 1 minus r over capital R. Let us continue the solution here. So volume now equals, we can put h outside. By the way, capital H and capital R here are considered constant. So h, okay, pi times h, let us put capital H outside. Then insert r squared in the solution. So we have now r squared. R squared times 1 is r squared minus r squared times small r over capital R. So we have r cubed over capital R. We can now find the derivative of this solution. So let us solve dv over dr. So you still have pi and capital H. The derivative of r squared is 2r, and the derivative of r cubed over r is 3r squared over r. So step number 5, reduce. Step number 5, after differentiation, equate to 0. We can cross multiply pi and h to the other side, so it will yield to 0 also. So the remaining parameters in our solution is this, 2r minus 3r squared over r. Let's continue the solution. We have 2r equals 3r squared over r. So we can cancel 1r in the left side, 1r in the other side. Solving for small r, it will give us 2 times capital R over 3. Therefore, in finding the radius of the cylinder, the maximum cylinder inside the cone is equivalent to the 2/3 of the radius of the cone. So R equals 2/3 of capital R. So let us now find the solution for height of the cylinder, which is the small h. Small h is equivalent to capital H times 1 minus small r. We already have small r now, and it is 2/3 of capital R over capital R. Cancel this capital R, so we have capital H, then 1 minus 2/3 is 1/3. Therefore, small h, which is the height of the cylinder, is equivalent to 1/3 of capital H. Capital H is the height of the cone. So this is simply, small r is 2/3 of capital R, small h is 1/3 of capital H. These are the shortcut for this type of problem. Example number 5. This example is the continuation of example number 4. So we are going to use the shortcut we derived from equation or from example number 4. This is in finding the volume of the largest cylinder. So when we say cylinder, it has a radius of r and height of h. So the volume is pi r squared h. And if this cylinder will be cut from a cone, so let us illustrate the cone. This is the cone with radius capital R equals 6 meters. And the height of this cone is capital H, 9 centimeter. So from example number 4, the derived formula for the radius. The radius of the largest cylinder inside the cone is 2/3 of the radius of the cone, which is 6. So 2/3 of 6 is 4. Then for the height of the cylinder, it is equivalent to 1/3 of the height of the cone, which is 9. So this is 3. So let us substitute R and H to the volume of the cylinder formula. So this is pi times radius squared, and this is 4 squared. Then H is 3. Therefore, the volume of the cylinder is 16 times 3 is 48 pi cubic meter.